So here we have the first problem of review. They want you to compute this limit, okay? Limit of 2x over x minus 16 as x approaches infinity, right? Now we set up this method, this procedure. We said identify the largest power on the denominator, which is in this case x, right? And then we said then divide by x all the terms from the numerator, all the terms from the denominator, right? This way. This is the traditional method that we follow, and then I will show you the alternative using L'Hopital's, okay? This is limit of what? 2 over x into x is 1. This is 16 over x, right? And you are still taking the limit as x approaches infinity, right? But we know that the limit as x approaches infinity of 16 over x, since x is a huge number, must be thought as a huge number, right? Think of x being a million into 16 is 0.00016, right? 0. So this guy goes to 0, right? Goes to 0. So finally, you end up with 2 over 1, and that's the answer, right? 2. This guy, right? Great. But now, the question is, right, can we shorten this? Can we shorten this? Can we somehow use a different method so that this can be done faster? And the answer for that question, guys, is yes, we can use L'Hopital's now, L'Hopital's. So here, alternative, here, right here, alternative, using L'Hopital's. L'Hopital's rule. Remember, L'Hopital's rule said that if you plug into this infinity here and you get this expression infinity over infinity, one thing you can do is this: you can take the derivative of this guy, right? The derivative of 2x, and you can take the derivative of x minus 16, right? And you can trade this quotient by the quotient of the derivatives. Derivative of 2x is 2. Derivative of x minus 16 is just this invisible 1, right? And if you try again, the limit here is clearly just 2, right? So I think it's quicker, right? Quicker. You don't need to do this using L'Hopital's rule. So in case you want to use L'Hopital's rule, feel free. What matters is that you identify the right answer, right? Great, great, nice. Excellent. This one's similar, right? But I'm going to do it quickly just using L'Hopital's rule, right? Using L'Hopital's rule, as I explained there. This limit, the limit as x approaches minus infinity of x over 6x minus 10 should be equal to the limit of the derivative of x is 1, derivative of 6x minus 10 is 6, right? And this as x approaches minus infinity, and this is just 1 over 6, right? Using L'Hopital's rule. So quickly, right? Using L'Hopital's rule. Very good, right? Great. Or you can use this other method too if you feel more comfortable using this traditional method, right? Dividing this into this, into this. Feel free. Right, now this one similar, right? But again, using L'Hopital's rule, quickly you can say that this guy is just the same as the limit of the quotient of the derivatives, right? Right, derivative of the numerator 3, derivative of the denominator 16. So quickly 3 over 16, right? So you can see, guys, so now we have more tools. We can go over this faster, right? Yeah, great. Now, this one's similar. Look, I'm going to use L'Hopital's rule. Using L'Hopital's rule. What should be the limit as x approaches infinity of 2x plus 1 over 13x squared minus 7? Using L'Hopital's rule, this should be the same as the limit of the derivative of 2x plus 1 is just 2. Derivative of this guy, 13x squared, is 2 times 13, 26x, right? Derivative is 0, right? So I end up with this, right? But what is this limit? Well, this is just 2 over 26 times infinity, right? But what is this guy? Infinity into 2 is 0, right? 0. This is infinity. Infinity into 2, 0. Follow, guys? Yeah, again, I'm using L'Hopital's rule, right? You can use the other method too. It is equivalent, okay? Try to just do it efficiently, faster. Another one, can you try this using L'Hopital's rule or using the traditional method, right? Try to do this, guys. Do that. Let's write this out, right? Limit x approaches infinity of x squared plus 7 over x cubed plus 10, right? I still didn't figure this out using L'Hopital's rule or using the other methods, right? Number 5. Julian, very good, very good. Excellent, excellent. Number 5. Yeah, excellent. You got it. Yeah, basically, right? If you use L'Hopital's rule, you can trade the quotient of the functions by the quotient of the respective derivative, right? Derivative of this guy, 2x. Derivative of this guy, 3x squared. Simplify right now. Simplifying. 1x cancel, 1x stays, right? But this limit, right? Remember, it's just this, 2, 3 times some huge number, right? You think of replacing here a big number such as 1 million, 1 billion, that will make this quotient 0, right? So 0 to infinity, 0. Final answer. Excellent. Yeah, this guy is the same. I will leave it to you for you to do it at home. Similar. Let's look for new forms, right? Similar. And if I'm skipping something that you feel like we should do, let me know. We will do it, right? Use just L'Hopital's rule. We'll see that quickly you can get this done. This one, the same, right? But perhaps this one I should show because it requires doing L'Hopital's rule twice, I think twice. What do you mean twice, Professor? Well, I will explain here. Look, if you have this situation, right, and you apply L'Hopital's rule, then what's going to happen here? The first time you take the respective derivatives, you will get this, right? Derivative here minus 26x plus derivative of 8x, 8. Derivative of 15, 0, right? And here on the denominator, minus derivative of this guy, 22x plus 7, right? And this is as x approaches negative infinity. But now, if you replace negative infinity here, you're going to get here infinity, again infinity, again infinity, or infinity, right? So it still is not well defined. So you apply L'Hopital's again, L'Hopital's rule again, right? So applying, right here, applying L'Hopital's rule again. Rule again. You will get the following. Take the derivative again, right? Taking the derivative again, you will get that this is minus 26 now, and this is minus 22, right? And dividing these two, negative and negative, they cancel, 26 over 22, which simplifies, once you divide by 2, simplifies to 13 over 11, right? 13 over 11, which is there. Yeah, very good, guys. So next, let's take a look at the next. So whenever you need to apply L'Hopital's rule twice, do it so, right? Do it so. You can apply L'Hopital's rule any finite number of times as you need, right? So this will be L'Hopital's rule again, L'Hopital's rule, similar, right? Similar. Let's reach the computation of the asymptotes. This one also similar, right? But sometimes maybe I should do this because this will lead to a very special result. It's not going to be a number here. Instead, it will be probably infinity or minus infinity. Let's see. Suppose you have this situation, 2y cubed plus 1, and over here 9y squared plus y minus 7, right? Minus 7. And we want to get this done. Yeah, we have a method, right, that tells us to identify the largest term, the largest power in the denominator, and dividing by that numerator and denominator and working this out, right? That's one method, but now we're trying to do this efficiently using L'Hopital's rule. Let's use L'Hopital's rule here. For L'Hopital's rule, you take the derivative, right? And you're gonna get the following. Derivative here of the numerator is 6y. Derivative of the denominator, 18y. Don't forget the square here. Plus 1, right? And this limits is telling us that y is approaching negative infinity, right? Yeah. But now, if you substitute negative infinity here, negative infinity square is infinity. Here, negative infinity plus 1 is negative infinity. Again, you get negative infinity, right? So apply L'Hopital's rule again. Rule again, right? As many times as you need it. So now, if you apply this again, this is going to be 12y over 18, right? Nothing here because the derivative 1 is 0. And this is a limit as y approaches negative infinity, right? Now it's better because now if you substitute your negative infinity here, you're going to get 12 times negative infinity over 18. 12 times negative infinity, right? And negative infinity divided by 18 is still negative infinity. So you get this, right? Yeah, great. Very good. That's for 13, right? 13. Very good. Now, in case you want me to do this, guys, using the traditional method, also let me know, okay? I'm just trying to get this done quickly and efficiently, right? So, but let me know, right? Let me know. Very good, very good. That's it. Next is this one is similar. You just have to expand, FOIL this out, and then you do what I did before, right? So let's write this here, similar. Just FOIL this out. Very good. Let's look for new forms. Aha. I found here something new. Find this limit with radicals. But what to do when you are supposed to take limits with radicals? Let's see. Remember, we have this nice property for limits that says that as long as you have continuity, you are allowed to do this. You're allowed to put the limit inside the radical, right? Inside the radical. You know, here x is very big. So for huge values of x, this function can be considered to be continuous because we don't have even trouble here on the denominator, right? So good. So what you do is this big square root, and then the limit goes inside, right? So when you see a huge radical applied to the numerator and denominator, simply insert the limit inside the radical, okay? So you will get this. And then for this, we have either L'Hopital's or the traditional methods. I'm gonna follow L'Hopital's, right? L'Hopital says that I can trade this quotient by the quotient of the derivatives, right? So taking the derivative here, this will be 32x. Taking the derivative here, this will be 2 times 49. What is 2 times 49? Let's find out in our calculator. 2 times 49 is 98. Okay, 98, so 98 here. All right, now this is what I get, right? Yeah, but then let's see what's going on here. Yeah, but there is an x here, right? 2 times this times x. Now, eliminating the x, you will end up with what? A square root of 32 over 98, right? Simplifying 32 and 98 divided by 2 each, you get 16 over 49, right? A square root of 16 is 4. A square root of 49, 7, right? 7. So that's it, 4 over 7. Very good, guys. Very good. That's for 15, right? 4 over 7. So when you see a radical, just put the limit inside and proceed, right, as usual. This is similar. So I'm gonna write similar. So we will pay attention to different forms. Similar. This one's similar. You just expand this, right? And do the same as I did before. But sometimes students ask me, right, what happens if we have this multiplication? What to do, professor? Well, expand. I will do it. So limit as x approaches infinity of radical here 64x squared plus x minus 3. Over here, if you FOIL this out, x squared, x times 1x, negative 17 times x minus 17x, and negative 17 times 1 minus 17, right? This is what we get. Simplifying further, meaning combining like terms in the middle, you should get this 64x squared plus x minus 3 on the numerator. On the denominator, x squared. 1x minus 17x is just negative 16x, right? Minus 17. This is what you get. And now, again, right? Big radical here, put the limit inside the radical, right? And things should be back to normal here because now we have L'Hopital's rule to deal with this, right? So use it. What is good about L'Hopital's rule is very practical, right? So its application is very straightforward. So trade this quotient of functions by the quotient of their respective derivatives. Derivative of the numerator will be 2 times 64 is 128x. Derivative of x is 1. Twice x, derivative of x squared, minus 16, derivative of 16x, right? But turns out if you replace here infinity, again, infinity here, so it means that you have to apply the L'Hopital's rule again, right? Let's apply it again. So this will be equal to the limit as x approaches infinity of, don't forget the big radical here, derivative of this 128, derivative of this 2. But what is that? 2 into this guy is 64, right? So you end up with the square root of 64, which is just 8, right? 8. So that's it. That's 17. Yeah, very good, guys. So that's how you deal with this product. If you encounter them, just expand, FOIL them out, and you should be back to normal here, right? Very good. The similar, let's try similar. Let's try to reach a different topic. This one, I would say, is not similar because the radical is applied only to the numerator, not to the denominator, right? And I gave you these techniques, right, using the square root of x squared, square root of t squared, but they're kind of not so easy to follow. But now the good news is that we have L'Hopital's, right? We have L'Hopital's rule, so we're going to use that. I can apply L'Hopital's rule here, right? Because if I plug this into, I get infinity over infinity, so green light for L'Hopital, right? But what does L'Hopital rule says? Well, if you cannot handle this, L'Hopital rule says trade or change this quotient of functions by the quotient of their respective derivatives. Let's start with this guy. What's the derivative of this guy? T minus 6. derivative of t is just 1. The derivative of 0 is just 1, right? Now let's take the derivative of this guy. Remember, recall, the derivative with respect to x of a square root of x is just equal to 1 over twice the square root of x, right? You gotta have this written somewhere, guys. This is very useful, this result, right? I'm gonna apply this result to use the chain rule, right? The chain rule says the derivative of the outside function, the radical function, is this, right? We start with that. That's what the chain rule says. Here, the inside function, 36t squared minus 216, right? Times the derivative of the inside function. But what's the derivative of this inside function? 2 multiplying 36, which is 72, right? 72 t, the derivative of this part 0, right? So this is it. And now, let's see if we can, at this point, apply L'Hopital's rule, right? Yeah. And if it is still infinity over infinity, look, if I put infinity here, infinity, if I put infinity, it's still infinity, so it's still infinity over infinity. So again, I have to use L'Hopital's rule, right? So let's just organize this. Infinity 72t, there is a 2 radical 36t squared minus 216. So applying L'Hopital's rule again, derivative of the numerator is 72 now, right? And derivative on the denominator is this 2 constant comes out. Derivative of this square root is 1 over twice the square root of this guy, right? 360 squared minus 216 times the derivative of the inside function, which is this 72t, right? Yeah. Yeah, I think this one is gonna keep me going. It's not gonna give me the answer if I use L'Hopital's, because again, this will come back to what we started with, I think. Yeah, so probably this one, for this one, we have to use the method that I gave you before, because the L'Hopital rule keeps giving me the same form given this function, right? So yeah, because this will go up here. Yeah. Yeah, so let's try to use now then the other method, okay? Yeah, so for this form, I think L'Hopital's might not work. So let's just remove this. And let's use the other method that I showed you, right? Yeah, so let's use the other method. The other method said you are supposed to use this fact, a square root of t squared equal t, right? For t positive, which is the case because t goes to infinity. And then we said we're gonna do limit of this guy, 36t squared minus 216 over this guy t, and this one also divided by t, right? But here, instead of writing t, you write this, the square root of t squared, right? So this is what we're gonna do. Now, notice this will become limit as t goes to infinity of this. Here, t into t1 minus t into 6 over t, which is good. And this radical in here, radical or square root of t squared into radical of 36t squared is just 36, right? Which is good. Minus this into this is 216 over t squared, right? Now, the good news, guys, is that these two goes to 0. This goes to 0 because t is huge, right? This goes to 0. And what is left? Just the square root of 36 over 1, which is just 6, right? 6. Excellent. Yeah, great. So 6. Yeah, sometimes L'Hopital's may not work, but most of the time, right? 95% of the time. So if it doesn't work, you have the other method that I show you, right? Using this fact, the square root of t squared is equal to t for t positive. Very good. For this one, let's use the same method, right? Let's use the same method. And let's follow the same method. They want you to compute the limit as x approaches infinity of this guy, 12x squared plus 7x plus 1 over a square root of 4x squared to the 4 plus x cubed. Very tricky, this one. This one, I'm going to use the fact that a square root of x to the 4 is equal to a square root of x squared squared. And since this is positive, this is just x squared, right? Since x squared is positive. Right? No matter what x is positive or negative, x squared is always positive. Yeah, so we're going to use this trick. So now we know that we have to identify the largest power on the denominator is x to the 4, but since there is a radical, it should be x squared, right? X squared. So what you have to do here is this: you have to divide both numerator and denominator by the largest power on the denominator, which was apparently x to the 4. But since there is a radical, you divide this 4 by a 2 is x squared, right? X squared, it's a divisor. Now, in the denominator, you're supposed to divide this guy by also x squared, but write it in this form, in its equivalent form, right? A square root of x to the 4, right? This is x squared. This way. All right, so then for this divided into this is just 12. Just 12 there, guys. So plus x squared into 7x, 1x cancels. You're left with 7 over x. X squared into 1, 1 over x squared, right? Over here, this guy into this guy is 4, but don't forget the square root, right? 4. This into this, simplifying 1 over x, right? 1 over x, but inside the square root, right? Great. Now, good news, this guy on the limit, since x is huge, x goes to infinity, this goes to 0. This also goes to 0, right? Because x is huge. Think of x being like a million, a billion, right? 0, 0, 0. What is left? What is left is 12 over the square root of 4. But this is 12, the square root of 4 is 2. And you get 6 as your final result, right? That's the limit. Yeah, here for these forms, guys, use the traditional method because L'Hopital's will put you into an endless loop, right? Yeah, that's not going to be good. So it's better this other method. Great. Yeah, this one's similar to the one that we just did here, right? Similar, very similar. So this one's similar. So let's look for new forms. This one's similar to the one that we just did, right? Similar with the radical on the bottom, right? Similar. And we have reached then now this part that deals with finding horizontal asymptote, right? Finding horizontal asymptote of these rational functions. Look, 2x minus 3 over x minus 6, right? They want you to find the horizontal asymptote, right? If any. But remember, we have a nice technique which consists of identifying what type of rational function is this, right? And that is gotten by looking at the highest power on the numerator, highest power on the denominator, right? And looking at the degrees of those leading terms, right? 1 and 1, degree 1, degree 1. This is what we call an equally or, yeah, equally heavy, I think we call it, right? Equally heavy rational function, right? Why equally heavy, Professor? Because degree 1, equally heavy. For equally heavy rational functions, we said that the horizontal asymptote is given by this equation, y equal, and you just pick up this guy and this guy. Professor, there is nothing on the bottom. If there is nothing, this means that this is an invisible one, right? So your horizontal asymptote should be just y equal to. The equation of your horizontal asymptote is y equal to. So this guy, right? You follow, guys? For equally heavy rational functions, that is what we do. Great. Now, sometimes they will give you something like this, right? So it's not clear what to do. In that case, I gave you this advice, right? Take the limit of this function as x approaches plus minus infinity. If you get a real number, then you are done. That's your horizontal asymptote, right? If not, you say no horizontal asymptote, right? But here, look, when you distribute the limit, we're gonna get that this limit is really just equal to this 2, right? Limit of a constant function 2, and this guy goes to 0, right? 0, because x is huge. Positive or negative will make this 0. So minus 0 is 2. So then you say horizontal asymptote should be y equal to, right? Should be y equal to. So this one. Very good. Another one. They want you to find a horizontal asymptote here. Who can tell me in the chat what type of rational function is this? Is this equally heavy, top heavy, or bottom heavy by looking at the degrees of the numerator and the denominator, right? So look at the degree here 2, look at the degree here 1, right? By looking at this, is this top heavy, bottom heavy, or equally heavy? Anybody can write on the chat? Or anybody can say it, right? What type of rational function is that? Top heavy, bottom heavy, or equally heavy? I see in the chat two students figure this out. Patricia, very good, very good. You made my day. Top heavy, right? Julian, also top heavy, excellent, top heavy. Why you say, Professor, that this is top heavy? Because the one on the top is dominating, right? It's dominating by looking at the degrees, right? 2 bigger than 1, so top heavy, top heavy. And we have a rule, right? If our rational function is top heavy, then we immediately say no horizontal asymptote, right? No horizontal asymptote, so you gotta go with this. You follow, guys? For if your rational function is top heavy, then you have to say no horizontal asymptote, right? No horizontal asymptote, yeah, no. Indeed, these type of functions, the top heavy ones, when the difference of these 2 degrees is 1, they show what is called a slant asymptote, right? But no horizontal asymptote. So you answer here with no horizontal asymptote. Very good. Now this one, anyone could tell me on the chat if this top heavy, bottom heavy, or equally heavy? By looking at these two guys, right? 2 and 2. Yeah, I see on the chat. Equally heavy, Julian, very good. Equally heavy, Patricia, very good. You guys made my day. Yeah, great. Equally heavy, right? Equally heavy, right? The same degree, 2 and 2. But the rule says for equally heavy rational functions, the horizontal asymptote is given by this equation. Y equal, you just pick up this guy and this guy, right? The leading coefficients, this is how mathematicians call them, leading coefficients. And then you should do the math. This will be y equal 3, right? This should be the equation of your horizontal asymptote, right? 1, 3, 3. Yes. That is 427. Very good, guys. This one. Anybody in the chat could tell me what type of rational function is this? Is this bottom heavy, top heavy, or equally heavy? By looking at the degrees. I see. The students are participating, right? By looking at these degrees, right? You look at this and this comparing, right? Is top heavy, equally heavy, bottom heavy? Patricia, excellent. Bottom heavy, right? Bottom heavy. Why? Because the bottom is the one that is dominant, right? So this is bottom heavy. So we have a rule. If the rational function is bottom heavy, then the horizontal asymptote is just this, y equals 0, no matter what, y equals 0, right? Because this dominates, this dominates so much that makes the whole thing 0, right? In the end, the limit. 28 is that. Very good, very good. Yeah, and then the others are similar, right? These are equally heavy, so you know what to do. So this is similar. Let's go over more. Okay, this is also the top heavy, right? Similar, so you know what to do. And now we reach this new topic, right? No more horizontal asymptotes. Now they say find the requested asymptotes of the given function. They give you this function, and they say find the slant asymptote. All right. This slant asymptote appears whenever your function is top heavy, but not only that, when that top heaviness is happening by this condition, the degree of this is just one more than the degree of this guy, right? One more. Yeah, one more. So, and that's the case, right? 2 bigger than 1 by 1 unit. So then we have a rule. We said that the slant asymptote will come out as the quotient of this guy ignoring the remainder, right? The quotient of this guy ignoring the remainder. So we're going to do what is called a division of polynomials, right? And when you hear this division of polynomials, guys, don't freak out. It's just like dividing numbers, right? I will remind you of this now. Remember, when you divide numbers, you pick some number of digits, right? And then you say, okay, this is enough to be divided by this, right? So you start there. First term on the dividend must be divided by first term on the quotient. So let's do it here for everybody to see. What is 28x squared divided by 4x? 4 into 28 is 7. X into x squared is x, right? 7x, right? That 7x, guys, has a place here on top of this guy, 19x, on top of the x term, so this 7x, right? Now, 7x must be multiplied by this whole thing. So 7x times 4x plus 1. What's that? 7x times this is 28x squared. 7x times this, 7x, right? That is what you write here, 28x squared plus 7x. Professor, these are always the same. Yeah, not a surprise. They're always the same. Now you got to subtract this from this, right? And remember, guys, I help myself to do this subtraction by distributing this negative sign over. This becomes negative 28x squared, and this becomes minus 7x, right? And I just deal with this and this. I forget about this. 28x squared minus 28x squared is 0. Always this, the result for this column 0. But 19x minus 7x is 12x, right? 12x. So let's write it here, 12x. Just like what you do with numbers, you bring down the next digit here, bring down the next term, 8, right? And repeat the process. 12x now divided by first term here, 4x. Let's write it that somewhere. So 12x divided by 4x, right? What's that? It's 3, canceling this 2, right? That 3 has a place here on top of the constant term, right? Plus 3, plus 3. Very good. And then 3 times this is this, right? But that is just gonna help me to get the remainder. But this, in this case, the remainder is irrelevant, right? I'm gonna continue, but you can just stop there and catch your asymptote here, right? It's there. But let's say you continue. This will be 12x plus 3, subtracting, minus 12x here, minus 3 here. I'm gonna get a remainder 5, right? But in this case, it's not relevant, right? What is relevant is this guy. So pay attention to this. This tells you that the slant asymptote, then slant asymptote is this, right? Asymptote is given by this equation. Y equal this guy, 7x plus 3. The quotient, no matter what, no one, doesn't matter the remainder, what you get on the remainder, right? What matters is the quotient. The quotient determines the slant asymptote, right? So that's it, right? Follow, guys? Yeah, so just do the division And don't worry about the quotient because what really matters is the slant. Don't worry about the remainder, sorry. Ignore it. The quotient determines the slant asymptote, right? So there you go. Very good, very good. Great. This one is similar, right? I will leave it for you to do it at home, right? Do the long division and the quotient will determine the equation of your slant asymptote, right? Mm, Perhaps this one we can do because it's different than that. It's a cubic polynomial on the top. And it's top heavy and the difference of the degrees is 1. So you have to do long division in order to find your slant asymptote, right? And we're going to do it together. So to demystify this, not a big deal really dividing polynomials, right? 1 plus x squared here. All right, so it start again always by dividing the first term of the dividend by the first term of the divisor. But allow me to rewrite this divisor. It's not well written, properly written. When you write polynomials properly, you should write the terms with the highest exponent first and the other guys following, right? Yeah. And you may say, Professor, this is not complete. Yeah, don't worry about the dividend not being complete. You should worry about the device. Don't worry about the divisor being incomplete. You should worry about the dividend being complete, right? The dividend is complete. Cubic term, quadratic term, linear term, constant term. So this is enough. This you can handle this not being complete. I will show you. All right. So start dividing the first term here by the first term here. Right, write this out somewhere. 7x cubed divided by x squared. Right? What's that? Well, 7 divided by 1 is 7. X squared into x cubed is x, right? 7x. That 7x has a place here on top of the x term right here. 7x. Next step, you have to multiply 7x times the divisor. So 7x times x squared plus 1. That's going to give you 7x cubed plus 7x, right? Plus 7x. And that is what you write here. Look, but write it cleverly. Look, 7x cubed, right? Keep in the order, right? Cube term with cube term, and then 7x. 7x here, right? It's tricky, this one too. Then you are subtract this from this, right? When you subtract, remember to help myself out, I do this. Distribute the sign, I distribute the sign, I get negative 7x cubed for this, minus 7x, right? And I deal with this too. I forget about this. This cancels 0. This guy stays. Look, 3x squared, right? 9x minus 7x positive twice x, right? Bring down the next term, 3. Repeat the process. Now this guy must be divided by this guy, right? Let's do it over here. 3x squared must be divided by x squared. X squared into x squared cancels. This is 3. This number 3 has a place here on top of the constant term, right? 3. Then you are supposed to multiply 3 times this whole divisor, right? Let's do that. 3 times x squared plus 1. It's going to be 3x squared. This is 3. That you write here below. 3x squared plus 3, right? Kind of in order, look, quadratic term, constant term. Then you're supposed to subtract. At this point, I already got what I wanted, right? This will define my slant asymptote, right? I'm talking about this guy, right? But in case you want to finish this, you can just do this, right? Minus 3x squared here, minus 3 here. Turns out this division was exact with 0 remainder. So this is the quotient. So he said, and then the slant asymptote will be this, y equal, you pick up the quotient, right? Remainder, do not worry about that. In this case was 0, right? So it's good, but this is really what determines your answer. So we're talking about this guy, right? Yeah, very good, guys. That was for 33. Very good. Next, this one is similar, right? So you can do it at home.
Hi, Professor.
Yeah, go ahead, Yulan. Yeah, go ahead.
Reminder should have a 2x, right? 2x.
Julian, excellent. Very good. There is some remainder, right? Yeah, very good. But what is important here is that remainder is irrelevant. So this will be still the answer, right? You follow, Julian? Yeah. But it's true. Julian said 2x supposed to be the remainder. True, right? Remainder.
Yes.
Mhm. Yeah, very good, guys, that you're following. Yeah, very good. It's good to be proper, right? But what if the remainder is relevant? Yeah, there was this 2x hidden there. Yeah, very good, excellent. Yeah, but this is the excellent. Great. Now 34, let's see. It's similar, so I'll leave for you to do it at home. Let's enter a new topic here. Graph the rational function. This function. Include the graphs and equation of the asymptotes, right? Again, guys, notice this guy is, when written properly, right? Let's write it here again. It's just a top-heavy function, right? And not only that, the difference of the degrees is 1. So it's top-heavy by 1 unit, right? Yeah. So this means that it has a slant asymptote, right? And that could help us to graph this, right? And indeed, they want you to find the slant asymptote, right? And all possible asymptotes. So first, kind of to give you some courage, you can say that by looking at the denominator, you can see that if you set this denominator equal to 0, you can find out that this has a vertical asymptote at x equal minus 2, right? Once you divide both sides by 2, minus 2. So at x equal minus 2, there's going to be a vertical asymptote, right? This is one thing. Yeah. Now, besides that, since this is top heavy, it will have what is called an slant asymptote. But to find that slant asymptote, you're supposed to do this long division, right? Now, this time, notice the numerator is not complete. The dividend is not complete. I'm going to complete it by adding this 0 times x. The x term was missing, so I am adding 0 times x. We discussed that in the lecture, right? We completed. The divisor is here, complete, don't worry. So we start by saying, okay, this must be divided by this. What's that, Professor? Well, don't panic here, but look, what you're gonna get here is this. It's sort of an unusual result, but isn't it true that this is 1 and this is gonna be minus 1/2 of x, right? Simplifying, x into x squared is x, right? So that has a place here. It's going to be put on top of the x term right there. And then you're supposed to multiply that by the divisor this way. 1/2 of x times 2x plus 4. What's that? 1/2 times 2, negative 1 here, right? So negative x squared. And here, negative 1/2 times 4, negative 2x, right? Yeah, this is this. Write this here. Negative x squared minus twice x. And then we're going to subtract this, right, from this. To help myself out with the subtraction, I do this, right? I distribute the negative sign over. Minus and minus plus x squared here, minus and minus plus 2x here, right? This and this, they cancel as usual, right? This cancel. This is just twice x. 0x plus 2x twice x. Bring down the next digit, not the next digit, the next term, properly speaking here, because we're dealing with division of polynomials, right? Next term comes down. Start the process again. Twice x divided by twice x. Twice x divided by twice x is simply 1, right? 1. That 1 has a place here on top of the constant term, right? Plus 1. Plus 1 here. 1 times this guy is going to be the same guy, right? Multiplication by 1 is the nicest operation in mathematics because it returns the same number, right? So it's just this guy, 2x plus 4, that must be subtracted from here, right? Yeah. To do the subtraction, I distribute the sign. I do this minus twice x minus 4. This cancels. This is negative 2, which is going to be the remainder of this, right? But remember, the slant asymptote Slant asymptote is given by this y equal, and you pick up the quotient, right? Whatever it is, regardless of the value of the remainder, right? This y equal minus 1/2 x plus 1. Now, as a hint, guys, I give you this. Notice that these two will determine the answer because this is the vertical asymptote, right? And this is the slant asymptote, right? So looking through the choices, which one is having these two? You see, minus 1/2 x plus 1 is slant asymptote, and this vertical asymptote, right? Right, you see, these two determine the answer. So this should be this. But of course, if you want to make sure that this is the one, you can graph this as I did in the lecture, right? This equation with y-intercept 1 and a slope negative 1/2, right? Rise 1, run 2, but negative, right? You can get this, and then you have to use test points, right? Test points here and here to determine if it's this curve, or maybe this curve and this curve, right? But when you do the test points, it will show you this. But I'm telling you, right, that the slant asymptote here and the vertical asymptote is the only choice that is showing both, right? So it should be this guy, right? As an exercise, you can continue using test points and verify that this is this part and this is this part, right? Very good. All right, let's see. I think we don't have time for more, guys. Yeah, so we're gonna stop here, but let's see if the next is similar. Yeah, this is similar, right? But maybe you can do this, still have a few minutes. Yeah, this one also, right? Quickly determine your vertical asymptote first, as we did before, vertical asymptote, right? Vertical asymptote should be what we get when you set your denominator equal to 0. This is the vertical asymptote, x equals 0. And what about the slant asymptote? Good news here, because this rational function has such a simple denominator divisor that the division is really straightforward. Look at this. It's 2 over x minus x into negative 2x is negative 2 minus x into x squared is just x, right? Remember, this part is the quotient and this is the divisor, right? So therefore, no divisor, the remainder, right? This I should right here. Remainder, right? This is the quotient. So because of that, then you can say that then slant asymptote should be this, y equal this, minus x minus 2, right? I'm gonna highlight this for you to identify this with this, right? Yeah, and then again, right, look for the choice that is saying that the vertical asymptote is this and the slant asymptote is this, right? Vertical asymptote x equals 0, slant asymptote minus x minus 2. This is it, right? This should be at A. Yeah, that for question number 36. Yeah, I think that would be a good way to do it. Of course, at home you can try to use test points and verify that the curve goes this way and this way, right? Using test point, for example, you can use test point 1 and minus 1 here, right? And verify. Very good, guys. So yeah, it's this. Very good. All right, we should continue with our review for exam 3. The last time I went up to question 33, I will continue. When I see that questions are similar, I will skip some questions, right? But in case you feel like it's important for you, what I'm skipping, let me know, and I will go over that question that that you think is important, okay? Just let me know. Question number 37 deals with the minimization of a function, right? And we know that we do it via derivatives. it says the velocity of a particle in feet per second is given by this equation, v equal t squared minus 9t plus 8, where t is the time in seconds for which it has traveled. Find the time at which the velocity is at a minimum, okay? So the velocity is given by this equation, right? T squared minus 9t plus 8, right? Plus 8. This is the velocity. Now, we know that in order to minimize this velocity function, we have to set the derivative of our velocity equal to 0 and solve for t, right? And solve for t. Solve for t. Welcome, Jason. Welcome, Julian. We just started with a review for exam 3, okay? So if you have any questions, just let me know. Welcome, Tiffany. Welcome all you guys who just joined. We are continuing with review for exam 3. All right, we said that we're gonna take the derivative of this function and set that equal to 0 and solve for t. Derivative of the b function is derivative of t squared to t minus derivative of 99, derivative of 80, right? And this derivative we should set equal to 0 and solve for t, right? Solve for t. So this tells us that 2t should be equal to 9, right? Once we cancel these two guys. And divided by 2 both sides, t equal 9 over 2, or equivalently t equal 4.5, right? If you use your calculator and divide 2 into 9. And in the end, you may attach the units. Time is measured in seconds, so 4.5 seconds, right? Which is here. Very good, guys. So let's continue then, okay? That was number 37. Number 38 is similar, so I'm gonna just write similar. So we can continue, okay? We can continue. We should move on. All right, so similar 38, you can do it at home. Let's go over 39. A carpenter is building a rectangular room with a fixed perimeter of 380 feet. What are the dimensions of the largest room that can be built? What is the area? The area, okay. Okay, so let's start by drawing a diagram that can help us to understand what we are supposed to do, right? There's a rectangular room that needs to be built. Let's call this width X. Let's call this length Y, right? And we are supposed to maximize area, right? Maximize area. How do you know that, Professor? Well, because they talk about getting the largest room, right? So maximize the area. But the area is equal to, just X times Y, right? X times Y, which is this area. X times Y, right? That's the area that we need to maximize, right? But there is a constraint. The constraint is that the perimeter must be fixed. No matter how you design this rectangular room, the perimeter, which is going to be X here, twice X, right? Plus Y here, twice Y. This should be equal to 380 feet, right? This is the constraint. But now from the constraint, we can isolate our variable y, right? By subtracting 2x in both sides. 2y, 380 minus twice x, right? And dividing both sides by 2, y ends up being just this. 2 into 380 is 190, right? Minus 2 into 2, 1, so this is x. Now, in case you cannot do these computations in your mind, right? Use the calculator, guys. Use the calculator. Sometimes the numbers are not that friendly. So this is the 190 I wrote there, right? Very good. All right, great. So y is 190 minus x, right? So now simply we are going to take this guy and replace this into our area function. Why are you doing this, Professor? Well, because I want to have my area as a function of x, not as a function of y and x, right? And we are studying calculus one. In calculus one, I have tools to deal with functions that depend only in one variable, right? It's functions like this, right? Later on, I said, right, if you take calculus 2, calculus 3, they will teach you how to work with two variables at the same time. This step probably will not be needed, but right now in calculus 1, we have to do this, right? Replace from the constraint equation the value of y and get a in terms of x. Next, we know what to do to maximize this, right? Set the derivative of your area function equal to 0 and solve for x. That's all, right? So the derivative of this function is 190 divided the derivative of the first term minus twice x, derivative of x squared, right? That should be equal to 0. Well, then solve this equation any way you feel comfortable solving it. So I'm going to subtract 190 in both sides and then divide both sides by -2. So I end up with 190 divided by 2, right? What is that? Well, 95, right? 95. 95. And in the end, you may attach units. We are measuring silence in feet, right? So 95 feet. That's the value of x, right? This guy, 95. But now they want the value also of y, right? Of y and the area also, right? But if x is 95, then y is equal to, from this constraint equation, right? It's just 190 minus x, but x is 95. 95 taking away from 190 is just 95. 95, you can check on your calculator, okay? And then the area will be x times y, right? So 95 times 95, and that is just the following. 95 times 95 is just 9,025, right? 9,025. 9,025. And in the end, you may attach your units. We are dealing with feet, so the area should come out in square feet, right? So clearly, therefore, the answer for this is here, right? It's a 95 by 95 rectangle, which is actually a square, right? A square. And I want you to notice that, guys. It's a square, right? So which tells us, right, that the best way to construct a rectangular room in order to maximize its area is by giving this rectangular room the shape of a square, right? Square. So I want you to notice that, right? So square. Right? It's a square. Right? We explained, right? If there are no constraints, if you are not using a wall to construct part of this rectangular region, then the final solution is a square. Keep that in mind. All right, great. So this one is similar. So I'm gonna leave this for you to do at home, okay? This one is similar. Next, let's move on then, similar. What about this 41? A rectangular field is to be enclosed on 4 sides with a fence. Fencing costs $3 per foot for 2 opposite sides and $2 per foot for the other 2 sides. Find the dimensions of the field of area 770 square feet. That would be the cheapest to enclose, cheapest. All right, they're trying to minimize the cost, right? There's a rectangular field here. Now notice that the cost for this part and this part is not the same as the cost for this part. So I shouldn't expect this to be a square anymore, right? So But one thing I can do is look, since we are trying to minimize the cost, right? It would make sense to spend on the longest side, the most expensive material, right? $3 per foot here, $3 per foot here. And the shortest size, it would make sense. Yeah, actually it's the opposite, right? On the shortest side, I should spend, or I should think of using the most expensive material, right, on the shortest side. And on the longest side, I should spend or use the cheapest material, right? This makes sense. Yeah, so now call this X, X, this Y, Y. These are the lengths, the side lengths of the rectangle, right? And then the cost should be what? $3 per foot here. I'm using X feet. So 3X, same here, 3X, right? The cost. So 6X in total, the cost, right? For these two guys. For these other two guys, $2 per foot here, Y feet, the cost will be 2 times Y, right? But 2 times Y again here, so 4Y, right? 4Y, that's the cost. I need to minimize this, right? Minimize this. Subject to what? Subject to what? This is the constraint, the restriction. No matter how you design this, the area, which is given by X times Y, right? The area should be equal to 770, right? 770. Yeah, very good. Square feet. Great. From this constraint, if we isolate our Y, right? Isolate our Y. So Y will be equal to 770 over X, right? This is Y in terms of X. And then we just take this guy and substitute it in here, right? So that we will have our cost function in terms of just one variable X, right? So cost function will be 6X plus 4 times Y, but Y 770 over X, right? Cost function will be equal to 6X plus, let's get this in the calculator, right? 4 times 770. And at the same time, let's write X on the numerator as X raised to -1, right? As X raised to -1. So 3080 here, 3080, X raised to -1, this guy, right? You may say, why, Professor, you're writing this as X raised to -1? The reason is I want to make this cost function look like a polynomial, right? This is not technically a polynomial. Polynomials do not have negative exponents, right? But it looks like a polynomial because polynomials are easy to differentiate, right? Remember, the next step to minimize this function is to set a derivative equal to 0 and solve for X, right? So the derivative of this function should be the derivative of 6X, 6. Derivative of this part will be -1 multiplying this guy is -30 or 3080, right? X raised to -1 minus 1 minus 2, right? This is the derivative, right? This is the derivative, this guy. And that derivative should be equal to 0, right? Should be set to be equal to 0, and we should solve for X to minimize this cost function. If you do that, notice if I transpose this term to the other side, changing its sign, I get this, right? This is the same as adding this quantity to both sides of the equation right here. Nothing get canceled, and here you get this, right? But this will facilitate solving for X using. Now, I'm gonna do this, 6 equal 3080 over X squared, right? I'm putting this back on the denominator, okay, to solve for X. Next, allow me to multiply both sides of this equation by X squared to eliminate my X squared, right? And I will end up with a 6X squared equal, canceling these two, 3080, right? Dividing both 6 by 6, both sides by 6, sorry, x squared will be equal to 3080 divided by 6, right? Use your calculator, right? I strongly recommend that you use your decimal scientific calculator, right? I get this guy, 5.13. Yeah, and then I have to get the square root. Yeah, but let's check everything. Let's check if everything is correct. Yeah. Yeah, 4 times this, negative 2. Yeah, I think it's correct. 513.33. Let's round it, okay? 513.33. Take square roots. Both sides, right? X equal the square root of 513 here. 513.33. I get 22.65, which rounded to 1 decimal place. You see the answers, they are all rounded to 1 decimal place. Is 22.7, right? 22.7. So let's write it out, 22.7. And then let's attach the units. We are dealing with feet here, so this should be feet. But once you have X, then you can immediately find Y, right? By looking at this equation. Y is equal to 770 divided by X. Then you say Y is equal to 770 divided by X, right? But what is that? Let's compute it in our calculator, 770 divided by 22.7. 33.9, 33.9, which can be rounded to 34, right? 34, 33.34, approximately 34. Right? And this guy, the X, goes with this price at $3 per foot, right? Price for the fencing. And the Y goes with $2 per foot, right? So look through, and then you will see that the answer is here, right? Very good. Look, 22.7 at $3 per foot by 34 at $2 per foot, right? Very good, guys. Yeah. Tricky problem, right? Because the cost is here and here is different than the cost here and here, but follow this slowly, right? Check your work always, and then you should be okay. This one is similar, okay? Similar. I'm going to skip. Try to do it at home. Follow the same method, is equivalent. Let's go over 43, okay? Okay, 43 talks about constructing a box from a thin piece of cardboard, 20 inches by 20 inches, square corners are cut out so that the size can be folded up to make a box. What dimensions will yield to a box of maximum volume? What is the maximum volume? Round to the nearest tenth if necessary. Okay, so start by drawing a square, right? And from that square, we're going to construct a box, right? A box by cutting on each corner of the square certain amount, which are going to be squares, right? With side lengths, we don't know in advance, so we're going to call that side length X, right? X here, X here. And by folding what is left, right? What is left after you cut that off in each corner, right? By folding this up, we should be able to construct a box, right? A box, which more or less is going to look like this, right? But what is important is that box, they want it to be, we want it to have maximum volume, right? Maximum volume. What should be X? so that this box has maximum volume? Well, let's find out, right? For that, we have to maximize the volume of this box, right? But if I fold this up, fold this up, right? Fold this up, the flaps, what should be this length? Anybody could tell me in the chat, this height, since we are folding everything up. Anybody could say in the chat or tell me? Based on our design right here. Imagine removing, and folding up. I can see. Very good, Jolan. Very good, Jolan. X, that's the key here. No matter what you do, if you are cutting off here X, squares with silent X, no matter what, the height has to be X, right? So we're folding this up. Now, what should be this guy and this guy? Anybody could tell me in the chat? Notice that originally the material that they're giving you is 20 inches here, 20 inches here, right? If you are removing twice X and X, what will be left for this and this? Yeah, try to catch that, guys, very important. Alexia, very good, excellent. 20 minus twice X, right? 20 minus twice X. 20 minus twice X here, right? Doing this X, 20 minus 20, and also 20 minus twice X here, right? Because we are dealing with a square shape here to construct the ball, right? Very good. Now volume of a cube is given by the width times the length times the height, right? That's how you compute the volume of a box, right, in general. So the volume is going to be the width, 20 minus twice X, times the length, 20 minus twice X, times the height, right? The height X, right? And now I'm going to expand this so I can get the volume as a polynomial function, right? Because later I will have to take the derivative, set it equal to 0, right? So let's expand this. Let's FOIL this out, okay? 20 times 20 is 400, right? 400. 20 times negative 2x minus 40x. Negative 2x times 20 minus 40x, again, right? Minus 40x. Minus 40x, and then negative 2 times negative 2, positive 4x squared, right? Positive 4x squared. That's this guy, right? But still we have to multiply by x. Notice if you combine these two like there, minus 40x, you're going to get the sum of these two with a negative sign in front of it, minus 80x, right? Minus 80x plus 4x squared times x, right? Multiplying x over, you're going to get v equal 400x minus 80x squared plus 4x cubed, right? You follow, guys? Yeah, very good. Someone is trying to join. Great. So now this is a cubic function, right? Cubic function. Now, next, I have to set my derivative, set the derivative of my cubic function equal to 0 and solve for x, right? This will tell us what x or what value of x will maximize the volume. So the derivative of x then will be what? Allow me to organize this cubic polynomial this way so that this will facilitate the computation of the derivative and also will facilitate solving the equation, right? Derivative equal to 0. Derivative of this first part, the cubic term, is going to be 12x squared, right? 12x squared minus 80 multiplied by 2, that comes down 160x, right? Plus 400, right? Plus 400. This should be equal to 0. I see some questions, some remarks. Yeah, it's okay, Ruth. It's okay. Yeah, if you have trouble with the internet connection, if it kicks you out, come back and I will let you in, right? It's okay. It's okay. Yeah, all right, great. So this is the quadratic equation that I have to solve now in general, right? Now, guys, in general, this is what you should do. Use the quadratic formula, right? Because sometimes students say, Professor, why don't you divide by 12 and you factor? Yeah, sometimes that might be possible, but sometimes might not be possible, right? So I'm trying to show you a method that will work no matter what, right? No matter what, the quadratic formula will work. But what is the quadratic formula, Professor? It's this formula that you should have handy somewhere. Is this minus b plus minus square root of b squared minus 4ac over twice a, right? This is called quadratic formula. And will allow us to compute two solutions for this equation, right? So let's do that in our Desmos calculator. All right, so now the first one, minus b, I'm gonna use a fractional form. So advice, click here. Start with minus b. What is b? B is this guy, right? Minus 160, minus 160. So minus 160, that's b. Plus, I start with plus and then we'll do with minus. Plus a square root of what? B again, within parentheses, right? Within parentheses, minus 160, which is b, square, minus 4 times AC. A is 12, C is 400, right? 400. Great. So this is this. On the denominator, twice A, right? Twice A, but A is 12. A is 12, right? 12. Okay, great. Okay, I get 10, right? 10. That is going to be one of the solutions, 10. And what will be the other solution? Well, just change this for minus, right? Minus. The other solution, 3.33. 10 and 3.33, right? Yeah, let's do 10, 3.33. Now, one of these solutions will make sense, the other will not. How can I check which one makes sense, which one does not make sense? Well, one quick way you can do that is by evaluating x into your volume function, right? Your volume function. You have a candidate 10 here and then 3.3 here, right? 3.33 here. Let's find out what's the volume for each of these guys, right? So you go back to your Desmos scientific calculator or any scientific calculator of your choice. And in this volume function, we're going to evaluate both, right? Number 10 first, and then 3.33. We'll see which one makes sense. All right, this is cube, don't forget cube for x cubed minus 80 x squared, but our x is 10 this time, right? 10 squared plus 400 times x, right? Our x is 10. Professor, what? 0? Yeah, not a surprise, guys. Not a surprise when you realize this. Look, if you are using 10 for x, right? 10 for x, this will be 10. 2 times 10 is 20, right? So 20 minus 20 is 0. So this will be 0, this will be 0. There's not going to be base, right? No base. So I cannot construct a box without a base, or base 0, volume 0, right? That's the reason why the volume is 0, right? Don't be surprised, 0. But however, if I use the other one, 3.33, notice that this one is not going to be 0. Instead, it's going to give me a meaningful volume. You see, 3.33. Because I'm using less than 10, right? So we will get some bucks. 592.59, right? Yeah, so this is meaningful, right? So let's write it out. 592.6, right? 592.6. 92.6, 592.6. This one was 0, right? So it means that this is the good one, right? This is the good one. This one, nonsense. So nonsense means ignore it, right? So keep this. So your answer will be x equals 33.33.3, right? Tiffany has a question. When at the end of 400 come off in the prime answer. Well, Tiffany, we are saying that we are taking this to be 3.3, right? Mhm. Yeah, the height, right? 3.33, right?
Right. Which one is your prime answer? Which volume?
Yeah, we'll specify that. Look, Tiffany, you agree the height is 3.33, right?
Yes.
Now, notice what will be the length here? This, right? We gotta calculate this guy now. Let's calculate in the calculator this, right? 20 minus 2 times 3.3, right? 3.33. What is that? It means that the this one 13.34 should be the length, right? 13.34, right? 13.34, this guy, 13.34. And this the same, right? 13.34, and this the same, 13.34. So Tiffany, then tell me, what do you think is the answer? And the volume is this, 592. About, yeah, so which one do you pick by looking at this? 3.3 the height, 13.34, 13.34, and volume 592.6. Which one would you pick as your answer, Tiffany?
B.
Yeah, right. You see? Yeah. So once you find this guy, the X, then find the length, find the width of the box, and then together, these three together, they will tell you what the answer is, right? They will tell you together. And the volume also, right? The volume, look here, right? This is cubic inches, right? You follow now? Everything okay, Tiffany?
Yes, yes, thank you.
Very good, very good. Yeah, very good, very good. It's a tricky problem, but it's a very common in the industry to maximize volume for packaging, right? So it's a very nice problem. All right, great. So this is how you handle this. Then the next problem is similar. So I want you to try this at home, similar. Okay. Is similar another construction box. Then we reach 45, which is this problem with the barn, right? Yeah, let's go over this together. Okay, so what does it say? It says, a farmer decides to make 3 identical pens, 1, 2, 3, right? With 104 feet of fence. The pens will be next to each other, sharing a fence, and will be up against a barn. The barn side needs no fence. So this part doesn't need material, right, for the fencing. What dimensions for the total enclosure, rectangle, including all pens, will make the area as large as possible? Will make the area as large as possible, right? Great. So let's take a look at this problem. So we are trying to maximize this area, right? This enclosure, right? And we are using the barn as this part of the enclosure, so we don't need material here. So we need material here. I'm gonna call this with X, 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 and X. And I need material here, I will call this Y. It's just me. I call the smallest distance always X, the longest Y, but you can switch. If you can call this Y, 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 this X, the answer in the end will be the same, guys, okay? All right, so now we have to maximize the area, right? The area, which is gonna be X multiplied by Y, right? The area. But there is a constraint. There is a constraint, there is a restriction that we must respect, a limitation. It is, no matter how you design this, the material should add up to 104 feet for fencing, right? For fencing. So 104 feet of fence should be the total. I'm using X for fencing here, X again, X again, X again. So 4X, right? Plus Y here, no matter what, should be equal to 104, right? This is called the constraint, okay? Now, this is the goal, right? To maximize this guy. This, right? Maximize area is the goal, right? And the constraint is 4x plus y equals 104, right? Now, guys, remember from the constraint, you are supposed to solve for y, right? So that you will have y in terms of x here, and you can replace this guy into your objective function, right? The one that you have to maximize, right? So therefore, we can have the area in terms of only one variable, right? Which is x in this case, right? Very good. So area will be equal to what? 104x minus 4x times x, 4x squared, right? It's a polynomial function, easy to differentiate, right? So now next step is simply set your derivative equal to 0 and solve for your variable x, right? That way you will find x such that this function gets maximized. So the derivative of this function should be just this. For the derivative of the first term, the derivative is 104, right? Derivative of the second term, 2 comes down, multiplying 4 is 8. X stays with 1 less here, raised to 1, right? And this should be equal to 0, right? Now, one way to solve this equation is by subtracting 104 in both sides of the equation, and then dividing both sides of the equation by -8, right? And I said this is just one way to solve this equation. There might be other ways. Follow whatever you feel comfortable with, guys. What is important is that after canceling the signs, you should get for x 13, right? 13 feet. 13 feet. That is the value of x that will maximize the volume. But this tells us that then y, the other dimension, right, should be what? I have here y in terms of x, right, here. So replacing my value of x that I just found, 104 minus 4 times the value of x that I just found is 13. I will get that the value of y is just this. Let's calculate this in our Desmos calculator. 104. 104 minus 4 times 13, right? Yeah. Great. So 52, right? 52 feet. This is telling me that if I choose x to be 13 feet and y to be 52 feet, the area that I will produce here will be maximal, right? It will be the maximum area possible. So this should be the answer, right? Now, these two things can be written as this: 13 feet by 52 feet, right? Or 52 feet by 13 feet is another way to write it out, right? Doesn't matter the order, right? As long as you present both dimensions there, you're fine. And this tells me that the answer should be this one, C, right? Yeah, everybody okay? Yeah, any questions? Just let me know. Very good, very good. So this is how you deal with this barn problem, okay? And this question is really similar. So we should probably skip this one, right? So similar. Or in case you want me to go over questions that I'm skipping during the break or before the lecture is over, you can let me know and I will come back to them. But it's similar. Try to do that at home. Now another form here, look. This is an application to finance. It says find the number of units that must be produced and sold in order to yield the maximum profit, given the following equations for revenue and cost. Revenue 50x minus 0.5x squared, cost 9x plus 10. Solution. First, recall that profit is defined as revenue revenue minus cost, right? That is the definition of profit, because it's basically what you get out of selling your items, right? The revenue minus what you spend producing those items, right? The difference is what you keep in your pocket, right? It's profit, right? Now let's represent this profit function with a big P, with a capital P. I'll put this big P here. Revenue function, let's represent it with R of X. Cost function, C of S, right? We have these guys given, right? They are given there. So let's pick them up from there. So profit function will be equal to revenue function 50x minus 0.5x squared minus, be careful here, for the cost function, I'm gonna write it within parentheses, why are you doing that, Professor? Well, I want to make sure that I'm not just subtracting 9x, but I'm subtracting 9x plus 10 altogether, right? So that's why parentheses here is a must, okay? Now, work this out, simplify it, right? If you simplify it, you will see that this is just minus 9x minus 10, right? Sometimes the students say, what are you doing there, Professor? Well, if you don't follow this, think of a negative 1 being there, right? And think of multiplying negative 1 times 9x, that's negative 9x. Negative 1 times positive 10 is negative 10, right? So you get this. Now, what I'm going to do next is I'm going to combine like terms. These two guys are like terms. They have the same variable part. So combining them, I get that my profit function will be negative 0.5 x squared. 50x minus 9x is just 41x, right? Minus 10. This is my profit function. It's a quadratic function, right? Now, next step, set the derivative of the profit function equal to 0 and solve for x, right? This is our method to maximize functions, right? So setting the derivative equal to 0, the derivative of this profit function will be the derivative of this guy is this 2 multiplying negative 0.5, 0.5 1 half, 2 times 1 half is 1. So I get just minus 1, right? Minus 1 x. What did you do, Professor, there? If you're not comfortable doing this in your mind, guys, just always play safe and multiply this. This is what I did, right, in my mind. So times 2, negative 1, right? And what happens is mathematicians don't write negative 1 when negative 1 is the leading coefficient, right? Yes, it's minus x. Very good. Derivative here is 41, right? Derivative of this guy is 0. I don't have to write anything. And that should be equal to 0, right? Now we're going to solve this for x. Allow me to subtract 41 in each side. Minus x equal minus 41. Dividing both sides by negative 1. Remember, there is an invisible 1 here, right? X equal 41, right? X equal 41. And the units here is just units because it's the number of units you must produce to maximize your profit, right? So this is here. 41 units. That's it. Very good, guys. So let's move on, right? Let's move on. This is number 47. 48 is similar, right? Of course, the revenue function, cost function are different, but the method to solve this is similar. So you should try this at home. Or we can go back to them on the break or before this ends. 49 is a little bit different. It says, well, I think we have done this also, right? It says just they give you the price of a computer and they are asking you to minimize it. In terms of minimize the price. Yeah, great. So similar. I will write as a hint here how to solve it. Set P prime equal to 0 and solve for T, right? For T. Yeah, great. This is good. This one's similar, right? Let's look for other forms, similar. This one is a little bit different because they deal with cost. instead of maximizing now, they want you to minimize the cost. So let's do this 51. If the cost of a computer system increases with increased processor speeds, the cost C of a system as a function of the processor speed is estimated at C equals 6S squared minus 2S plus 1,200, whereas is the processor speed in megahertz. Find the processor speed for which cost is at the minimum, right? So they are trying to minimize the cost of this function, right? This is a special function that depends on the speed of the processor, right? Which is measured by this letter S. Don't confuse this with 25 is 2 times S, right? 2 times S, well, my 1,200. Right, but the method to minimize this function is this, right? We set the derivative of our cost function equal to 0, and then we solve for the variable, which in this case is S, right? S. So let's do that. The derivative of this cost function should be 2 multiplying 6 is 12, 12S, right? Minus derivative here, 2. Derivative of this is 0. We don't have to consider that. And that should be equal to 0, right? To solve for S, I'm going to add 2 to both sides of the equation. I get 12S equal 2. Now, be careful, guys. Always when you divide both sides of the equation by a quantity, that quantity must be the one attached to the variable, right? Not the smallest, right? This the one attached to the variable is 12, right? So S, believe it or not, should be 2 over 12. 2 over 12, Professor, what's that? Well, you can simplify and say it's 1 over 6, right? But since the answers are shown here in decimals, right? What I'm going to do is I'm going to take my calculator and divide 2 by 12, or 12 into 2, right? I get this number, 0.0166, right? And I'm going to write 0.16, right? 0.16. But notice what happens when I round it to 1 decimal place. Notice that all the choices are expressed up to 1 decimal place. So if you round it, right? And this is something that sometimes students get confused with, but rounding, right? Rounding to 1 decimal place, then this becomes, right? If you round it up to here, 6 is bigger than 5, so it makes this a 2, 0.2, right? Yeah, very good. So that's it, right? Excellent. Someone commented something on the chat. Let me see. Excellent, Tawilda. Excellent, right? Yeah, very good, very good. Sometimes don't get confused, right? It's in the exam, right? Rounded, right? Because this will appear there, right? It's not 1.2, it's 0.2, because I'm rounding it to 1 decimal place, right? 0.2 megahertz, right? In the end, you attach the units, right? Megahertz. That's it. Yeah, excellent, excellent. Very good. So next question is similar, right? So I hope you can do this at home. Similar. Let's look for more forms. 53. This is another form. This is an optimization problem. It says a private shipping company will accept a box for domestic shipment only if the sum of its length, this guy, and girth, all this length around, right? It's like a perimeter of this square in this case, because they say, and the girth distance around does not exceed 120 inches. What dimensions will give a box with a square in the largest possible volume, right? Yeah, so we are supposed to maximize the volume, right? Which we are going to represent with V, right? But if we call this height X, this width X, and this length Y, what should be that volume? Notice this is a square, so this will be also X, this will be also X, right? The volume, remember, is in general the width multiplied by the length multiplied by the height, right? The volume of any box. But in this particular box, the width and the length are the same, right? So this will be x times y, right? Let's call y the height. So volume will be x squared times y, no matter what, right? Multiplication of the three main dimensions, x times y in any order, this will lead to this volume. Now, we have a constraint. They say, right, no matter how you design this box for the shipment, right, you're supposed to use or utilize 120 inches for the sum of the girth and the length, right? Because otherwise they will not ship it, right? They say the girth, the distance around here plus this length, distance around here is x plus x plus x plus x for x plus the length y, that should be equal to 120, right? 120 inches. So objective function constraint, right? Remember, from the constraint, we isolate our y. Y equal 120 minus 4x, right? I got y in terms of x for my constraint, and we know that this guy must be substituted into the objective function, right? So that we get our volume in terms of just one variable, right? In this case, x. Okay. Now multiply x squared over v will be equal to 120 x squared minus x squared times 4x cubed, right? 4x cubed. It's a polynomial function, cubic polynomial function, right? And the next step should be just to set the derivative of our polynomial function equal to 0 and solve for x, right? For x. The derivative of this function is 2 coming down, multiplying 120 is 240, right? X minus 3 comes down, multiplying 4, 12. 1 less stays here is 2, right? And this should be equal to 0, right? 0. Now, guys, we have to solve for x, right? One quick way to solve for x, one method that will always work, right, independent of this being factorable or not, is this: factor out x. Right here, factor out x. You may say, Professor, why don't we factor out 12x? You can do that too, but what if this is 13, this is 520? What if there is no common factor there, right? But x out will always work, right? So factor x out, right? X into 240x, 240, x into 12x squared, 12x, right? Now you are supposed to set each factor equal to 0. So x equals 0, one possible solution that quickly you see that does not make sense, right? If x is 0, there is no girth, there is no cross section here, the volume will be 0, right? So this one doesn't make sense, right? Ignore, right? Nonsense. Ignore. But this solution makes sense because look at this. If you solve for x, you will get that negative 12x is negative 240 here, right? Once you cancel these two. And dividing both sides by negative 12, x equal 12 into 24 is just 2, right? So 0, 0, right? Or you can use your calculator and get this, that x is equal to 20, right? So this guy 20, right? 20 what? 20 inches, right? Inches. From there, quickly find the value of y. The value of y, Professor? Yes, look at the constraint. From the constraint here, we got this for y, right? Y is equal to 120 minus 4x. So use that here, right? 120 minus 4 times x, but x we just found out is 20. So compute this, and this should give you the value of y, right? Such that the volume of the box it's maximum, right? So, or maximal if you want to say that way. Okay, so this is just 40, right? It's 80, taking away from 120, 40. 140. This one 40 inches, right? And when you look at the choices, you're supposed to express this box in this form, answer. This dimension by this dimension by this dimension, right? So start with 20, let's say 20 inches by 20 inches again, because again, X, right? And Y is 40 inches, right? 40 inches. So 220 is 140, right? Be careful there, guys. The choices might be tricky. So therefore, the one that you have to choose is this one, right? You follow, guys? Everybody okay, right? Another way is to identify this one with 20, this one with 20, and probably it will be easier if you feel like you should do this, and Y with 40, right? 140, 20, 20, right? It's like the three main dimensions of this box, right? Like I'm saying this is 20, 20, and this is 40, right? This defines the box, right? Uniquely. So that's the idea. So let's get ready to continue. This will be similar, okay? So similar to the one that we just did. Same idea. So let's try to focus on this one now. It's 55. Okay, time to come back. Let's try to finish this up. Question 55 deals with an application of optimization problems again. It says the following: if the price charge for a candy bar is P of X cents, then X thousands candy bars will be sold in a certain city where P of X is equal to 122 minus X over 16. How many candy bars must be sold to maximize revenue? All right, so let's start by finding out what is the revenue. What is the revenue? Remember, the revenue represented by R of X is what we get, the money that we get out of selling our items that we produce, right? So if we produce X items, in this case, X is measuring thousands of candy, right? If we produce X thousand candy bars, then what we're gonna get out of this is X times the price at which we sell each candy bar, right? So, but the price depends on X this way, 122 minus X over 16, right? Yeah, it's given there. So pick it up from there. This guy, right, goes here. Okay, great. Now, then let's compute our revenue function. This is what they want us to maximize, right? That will be 122x minus, this is 1 over 16, right? Times x squared, right? X squared. Now, set the derivative of revenue function equal to 0 and solve for x, right? This is how we maximize our revenue function, right? Solve for x. We don't have to put 0 anymore. Solve for x. Okay, great. So what will be the derivative of this guy? Derivative of this part will be 122, right? 122 minus what? Minus 2 comes down multiplying this 1 over 16, right? Times 2, x, right? X. And this should be equal to 0. Let's simplify a little bit here. 2 times 1, 2 over 16, x equals 0. And here, guys, you can solve this in many different ways. If you keep simplifying, this will be 1 over 8, right? X equals 0. Then you can transpose this to the other side, right? 1 over 8 times x. Changing the sign, right? And finally, multiplying both sides by 8, that should give you the answer, right? But this is just one way to solve it, right? There might be other ways, right? Some students, they just divide this and then move it over, divide this into this. It will work too, right? Either way you feel comfortable solving this should be okay. So finally, x should be equal to 8 times 100, 8 times 122, right? So let's do that. 8 times 122 is just 976. 976. Now, be careful, guys, when you attach the units. It's very tempting to think that the units should be candies, but in this particular problem, they are measuring for some reason the number of candies in thousands of candies, right? So follow that. This will be thousands candy, right? In thousands. So therefore, the answer should be this, right? Not this, right? This is 976 candy. This was 976,000 candy bars. This is the one, right? Be careful there, guys. Very tricky, the choices. Very good. Yeah, maybe we should highlight this, the 1,000 candy. All right, great. This one is similar. You should do it at home. Follow the same strategies. Completely similar. Let's look for new forms. What about this guy? 57 says, the altitude h in feet of a jet that goes into a dive and then again burns upward is given by this function h equals 12t cubed minus 198t squared plus 9,500, right? Where t is the time in seconds of the dive and turn, right? What is the altitude of the jet when it turns up out of the dive? What is happening here? Well, basically, this is an airplane. It's coming down, diving, right? But at a certain point, goes back up like this, right? Yeah, that's the whole idea of this problem. So what they're asking you to do is to figure out when this happens, right? At what time this happens. And after that, figure out what is the height then, right? At what time this happens, and then what is this age minimum, right? Minimum age, minimum height. So no problem, because we have a technique in order to minimize this height, right? This height, we set the height function equal to 0 and solve for t, right? For our variable t. Let's do that first. That will give us the time when this happens, and then substituting that time here, we'll get the age minimum, right? Minimum. Right. So derivative of age is 3 times 1236 t minus 2 times 198. 2 times 198, right? Let's see what's that. It's 396. 396. This is t squared, this is t, right? One less exponent. Plus derivative of this guy, nothing, 0, right? This equals 0. From there, let's factor out t. So we will be left with 36t, right? This into this, minus this guy into this guy, t cancels, 396, right? Equals 0. Setting each factor equal to 0, clearly we see that this is a possible solution, but does not make sense, right? Does not make sense that t equals 0, right? At time 0, no, not a good solution, right? But this one, this little equation, nonsense. So we ignore this, right? This one may lead to something good. 36t equal, remember, if you transpose this to the other side by adding 386 to both sides, this leads to 396 divided by 36, right? Dividing both sides by 36. So T, the time that will minimize the height is this, 396 divided by 36, right? And that is 11, very good, 11. So after 11 seconds, the height will be minimized, right? But in this particular problem, they want that height, that minimum height as a value, right? So then you substitute T11 into your age function, right? Height function here. 12 times 11 cubed minus 198, 11 squared plus 9,500, right? Yeah, that will be the minimum height. So let's compute it together in our calculator and using this Desmo scientific calculator OER material, guys, for you to use free. Okay, square plus 9,500, right? And I get 1,514. 1,514. Let's attach the units feet, right? Feet. 1,514 feet is the minimum height, right? That's it. Very good. All right, great. This is similar. Yeah, I think we did this one in class. Yeah, probably I can do it. It's not similar, it's different. It deals with maximizing the area, right? The area of a box, the what is called the surface area. Let's do it quickly. The company wishes to manufacture a box with a volume of 44 cubic feet, a box, right? The volume is fixed with open top, and which is twice as long as this is wide. So twice x here, right? Twice as long as it is wide. The height, I don't know, let's represent it with y. Find the width of the box, this guy, that can be produced using the minimum amount of material round to the nearest 10. Minimum amount of material, meaning that this part needs to be minimized, right? This part needs to be minimized. The area here, right? Minimize. Nothing on the top, so don't worry about that. All right, so therefore, the area here should be xy, right? The area here. The area here, multiplying this guy times this guy, 2xy, right? 2xy, the area here. The area in the bottom will be the multiplication of these two. So if we represent the surface area, right, to build this, to construct this box as S is going to be the area of the base. The area of the base will be 2x times x, right? Plus twice this, because there is one face here, the other face on the back, right? So twice xy plus twice this two, because this one face here, one face on the back, right? For twice 2xy. So this is what we are supposed to minimize. X times x squared plus 2xy plus 4xy. Notice this together. 6xy, right? Together. All right, now I have a constraint. I have to construct this box subject to this. They want the volume of the box to be 44 cubic feet, right? So the volume must be 44 cubic feet, right? So, and where is the volume here? Look, the volume is this guy, twice x multiplied by x, the width times the length times the height times y, right? So this is telling me that y multiplied by 2x times x, 2x squared equal 44, right? Right? Simplifying it. And then dividing both sides of this equation by 2x squared, sorry, I can isolate my y, right? This cancels. Y equal 44 divided by 2x squared, which is the same as 22 over x squared, right? 22 over x squared. Now, this guy substituted into here, into your s function, so that we can have s depending on just one variable. So s will be equal to, yeah, better here, right? Yeah, s will be equal to what? S will be equal to, yeah, here. 2x squared plus 6x times y, 22 over x squared. That's s. 2x squared plus 6 times 22 is this. 132, right? 132. So let's write 132 here. Look, 1x cancels, 1x stays, but I'm going to write that x up here as x raised to minus 1. So this is the function that I have to minimize, right? To minimize the material. So set s prime equal to 0 and solve for x. If you do that, the derivative is going to be 4x, derivative of the first term here for x, minus 132, x raised to minus 1 minus 2. That should be equal to 0, right? Should be equal to 0. Good. So let's do that. So there, for x, moving these terms over, right, or transposing it to the right side is this. Notice here for x will be equal to 132 over x squared, multiplying both sides of this by x squared. Let me be very close to the solution now. Notice 4x cubed equal, look, this cancels, 132. X cubed equal, dividing both sides by 4. This is, I think it's 34, but let's just do it in the calculator. 132 divided by 4, 33, 33, 33, very good. So 33, but notice now, x therefore will be the cube root, right? Cube root of 33. So you take the cube root, you will get the following, cube root of 33. Notice here in the decimal calculator, choose this function, put in the index at 3 because you are taking cube root. Cube root of 33 is 3.21. 3.21. 3.21. And that should be it. 3.21. Now, guys, remember, you have to approximate to the closest here. The closest to 3.21 is this guy, right? So this should be it, okay? Because there are a lot of computations there. Exponents are very sensitive to little changes. So just take the one that is the closest to what you get. And this is good, 3.4, right? The closest. Very good. Yeah, this in case it appears. Now we're done with the optimization problems. Let's go ahead with the L'Hopital rules. And then I think we have to go over Newton's method too. L'Hopital's rule deals with this type of limits, the ones that are undefined when you attempt direct evaluation, right? You attempt direct evaluation, notice you get 2 squared minus 4. Let's do the direct evaluation here on the bottom, so you can use the L'Hopital rule here. 2 squared minus 4 over 2 minus 2. 2 squared is 4, 4 minus 4, 0, 2 minus 2, 0, right? 0 over 0, undefined. So L'Hopital's rule says that whenever that happens, you are allowed to change this quotient of functions by the quotient of their respective derivatives, right? So you take derivative here, take derivative What's the derivative of this guy? Twice x, right? Take derivative here. Derivative of this guy is just 1, right? And L'Hopital says, then try the substitution again. Now you see that when you try again, it works. It gives you 4, right? 4, and turns out that's the answer. You follow, guys? 59, answer 4, using L'Hopital's rule. You may say, Professor, we can factor and simplify. Also yes, but eventually, like in this example, for instance, you might not be able to do that, right? So let's get to this. This one's similar, right? Okay, so use L'Hopital's rule, get the answer. But this one, I think if you try to factor, you might not be able to factor this polynomial in the numerator. Is a cubic polynomial. So this one, L'Hopital's rule. So how do we apply L'Hopital's rule here? Well, again, right, if you try to substitute the 1 directly there, you will notice that you will get 1 cubed minus 5 times 1 squared plus 4 all divided by 1 minus 1, right? But this, when you compute in the calculator, 1 minus 5 is minus 4 plus 4 is 0. 1 minus 1, 0, 0 over 0, right? Yeah, don't get discouraged when you get 0 over 0. Apply L'Hopital's rule. L'Hopital's rule says you are allowed to change the quotient of these two functions by the quotient of the derivative of these two functions, right? The derivative of the function in the numerator is 3x squared minus 2 times 5, 10x. Derivative of this function 1. And L'Hopital says try again. Try the direct evaluation again. And you will see that it works now, right? So 1 squared is 1 times 3, 3. 3 minus 10 minus 7, right? The division by 1 means nothing. So minus 7, giving us as an answer this guy. Very good. Now, L'Hopital's rule can be applied not only to rational functions, but also to functions that contain these trigonometric functions, right? Such as this, for instance. Look, if you try direct evaluation, you're going to get this times 0 minus 1 over 0 squared, right? But what is that? Cosine of 0 is 1. So you get 1 minus 1 on the top, 0 on the bottom, 0 over 0, right? So, which means that you can apply L'Hopital's rule, right? L'Hopital's rule says take the derivative of this guy. That's going to be derivative of cosine of 3x is derivative of cosine minus sine, right, of 3x times derivative of the inside function 3x, 3, right? Derivative of this guy 0 over derivative here 2x. Now, L'Hopital says try again. But if you try again, you're going to end up with this sine of 3 times 0 times 3 over 2 times 0. Sine of 0 is 0. 0 times 3 is 0. 0 times 2 is 0. 0 over 0 again. Don't get discouraged, guy. Apply L'Hopital's rule again. Again. So take the derivative again of this. Derivative of this again, derivative of sine is cosine of 3x, right? Times the derivative of the inside function 3. There is another 3 there, right? Constant. This derivative of 2x2. Try again. But this time, the difference is that this time is going to work, right? So this times 3 9 over 2. Cosine of 3 times 0 is 0. Cosine of 0 is 1. 1 times 9, negative 9 over 2. Negative 9 over 2. Right? Yeah, very good, very good. Negative 9 over 2. Yeah, very good, very good. So, great. Let's move on. Let's move on. Yeah, great. It fixed itself. So now 63. This one, another application of L'Hopital, right? Again, quickly take derivative on the numerator, the denominator, because if you replace this, you're going to get 0 over 0, right? I will leave this for you to do. Instead, we're going to apply quickly L'Hopital's rule here. This will be equal to a limit as x approaches pi over 3. Derivative of the numerator is this, derivative of cosine minus sine of x. Derivative is 0. Derivative here is just 1. Now, L'Hopital says replace or apply your direct evaluation again, right? Don't forget the minus. And this should be your answer. What is sine of pi over 3? Sine of pi over 3, if you look at the unit circle, in the unit circle, pi over 3, for pi over 3 here, look, sine, second coordinate, right, is square root of 3 over 2. Square root of 3 over 2, right? This is sine of pi over 3, square root of 3 over 2. So minus is square root of 3 over 2. Yeah, so now sometimes students ask me, where is that sheet, Professor? When I teach pre-calculus, I include this sheet, but I'm gonna send it to the chat right now so you can have it. In case you don't know by heart what is sine of pi over 3, right? Yeah. So let me put it in the chat. Yeah, here it is, the unit circle sheet. Okay, so yeah, let me. Yeah, for everyone. Yeah, you can get it from there, the unit circle with the values of sine, cosine. Yeah, great, in exact form, right? Very good. That's it. Now this one, let's figure this out together. Let's see. Yeah, great. So again, apply L'Hopital's rule. Trade the limit of this function by the limit of the respective derivatives. Derivative of x1, derivative of cosine is cosine of x, right? And try again. That's what L'Hopital says, right? Try again, 1 over cosine of 0. Cosine of 0 is just 1, right? 1. Sometimes Professor, cosine of 0, 1. Guys, if in case you don't remember that fact, cosine of 0, 1, right? In degrees or radians, doesn't matter because 0 degrees same as 0 radians, right? So good. This is good. Very good, very good. Moving on, let's see. Yeah, I think this one also L'Hopital's rule. Quickly change this quotient by the quotient of the respective derivative. Derivative of 5x is cosine of 5x. Cosine of 5x, the derivative of the outside function, derivative of the inside function 5, right? Derivative of sine, cosine of x. L'Hopital says try again. And using L'Hopital's rule, now you will see that it's gonna work now. It's no longer gonna be undefined. Instead, cosine of 0, remember we said is 1. Cosine of 0 again here, 1. 1 times 5 divided by 1, 5. All right, great. 66 is similar. So just use L'Hopital's, right? I want to make sure that I reach to the Newton's method. This one a little bit different. So we're going to apply L'Hopital's rule because if you try direct substitution, direct evaluation, directly, you will get sine of 0, 0, tangent of 0, 0, 0 over 0, right? That is the green light for L'Hopital's rule in case you get 0 over 0. L'Hopital's rule says this limit is the same as the limit of the quotient of the derivative of each of these. Derivative of sine of 5x is cosine of 5x, derivative of the outside function, times derivative of the inside function 5, derivative of tangent of 4x, derivative of tangent of 4x, remember, is secant square of 4x, times derivative of the inside function 4x, 4, right? 4. Now L'Hopital says try again, try the direct substitution again. So this will be cosine of 5 times 0. So you're going to cosine of 0, right? This secant square of 4 times 0 times 4. But this is cosine of 0, which we know is 1, right? Times 5 outside. Here, secant square of 4 times 0, 0 times 4. Cosine of 0, we said is 1, right? Secant is, recall, right? Secant of 0 is 1 over cosine of 0. But since cosine of 0 is 1, then secant of 0 is also 1, right? So this will be 1 squared, right? 1 squared. So 1 here disappear. 5 over 4 should be what is left, right? 5 over 4. So that should be the answer for 67. 5 over 4. 4 over 5 or 5 over 4. Let's see. 5 over 4, I think. Yeah, 5 over 4. This one. Very good. Yeah, great. Another one with L'Hopital. Probably we should do this quickly and then move to the ones with Newton's method. But let's see. This one has a strange form here. Sine of theta raised to a 7 power over theta, right? And this is the limit as theta goes to 0 here. Okay. Again, if you substitute directly, you will get that this is going to be equal to sine of 0 to the 7, which is just sine of 0, right? Sine of 0 to the 7 over 0, sine of 0 over 0, 0 over 0, right? Undefined. But L'Hopital says, don't panic, just do this. L'Hopital's rule using L'Hopital's rule, right? This will be equal to what? The limit as theta approaches 0 of the quotient of the derivative, respectively. Derivative of this guy is derivative of sine cosine of theta raised to 7 multiplied by the derivative of the inside function. Derivative of this inside function theta to the 7 is 7 theta to the 6, right? And all over derivative of this guy. Derivative of this guy is 1, right? And then L'Hopital rule says try again. If you try the direct substitution again, notice that now this should work. This is cosine of 0, which is just 1. And this is 0 to the 6, 0 times 7, the whole thing is 0, right? 0. Very good. So this guy for 68. Great. There are more examples here of L'Hopital. But let me say this is just similar, right? Take derivative of the numerator, derivative of the denominator, and then try again. This is what L'Hopital is all about. This one the same, right? Perhaps I should do this because, and then we will go over the Newton's iteration. Yeah, what if they ask you to compute this limit of 15x to the second minus 7x plus 4 over 6x squared plus 4x plus 17 as x approaches infinity? Well, if you substitute infinity there, you're going to get infinity here on the top, infinity on the bottom. L'Hopital says, don't worry, in case you get this, try this. Take derivatives, top and bottom. This is 30x minus 7. Derivative here, 12x plus 4. Try again. But if you substitute infinity again, you will get infinity over infinity again, right? So L'Hopital says, continue taking derivatives. Derivative of the numerator 30, derivative of the denominator 12. And that's it, because this is meaningful and this is something that you can take as your answer, right? Of course, simplify. Probably you can divide by 3 here, 10, divide by 3 here, 4, right? 10 over 4, divided by 2, 5 over 2. And this is here. Very good. Yeah, that's that. And this is similar. This is a different form. Yeah, probably we can take a look at this. What if they give you something like this? Remember, in order to apply L'Hopital, you need a quotient of two functions, right? There is no quotient, professor, here. It's instead a multiplication. But in class, in the lecture, we explained that whenever you have this form, you have to substitute this form by the following: sine of 4 over x divided by, you take the reciprocal of this, divided by 1 over x, right? These two guys algebraically the same, right? When you divide by 1 over x, you multiply by the reciprocal x. So these are the same. But however, this one allows you to apply L'Hopital. So because this is limit of sine of 4x raised to minus 1 over x raised to minus 1, right? Take derivatives in both sides. Not both sides, the numerator and denominator, right? Take derivatives and then apply L'Hopitals. Yeah, it's okay. It's okay. Totally, it's okay. Yeah, we're gonna do next Newton's method then. Okay, you got it. Cosine here, cosine of 4x raised to minus 1 times derivative of this minus 4x raised to x minus 2. On the bottom, derivative minus x raised to negative 2. These two guys cancel. And substituting here again, we get that cosine of 4 over x, but x is infinity, so this is going to be 0, right? Cosine of 0 is just 1, right? And there is a minus 4 there, so this will be minus 4. Yeah, let's go ahead and let's try the negative and negative cancel, right? This negative and negative cancel, so just 4, positive 4, 75. Yeah, this is L'Hopital's rule, but let's check Newton's method once and for all, because I want to make sure that you guys have an idea. This is similar. Try in the lecture, their example, right? But where is now Newton's, Newton's method? Here. Yeah, let's say this 83, okay? How, using Newton's method, you find the solutions of the equation f of x equals 0, right? They're gonna give you an equation. They're gonna ask you to apply Newton's method in order to find the zeros of this equation, or the solutions of f of x equals 0, approximately, right? Yeah, so how this goes? It's an iterative method, right? And it goes like this. X to the n is equal to n plus 1, right? Plus 1 is equal to the previous x to the n minus the function evaluated at x to the n divided by the derivative evaluated at x to the n, okay? So here they want you to generate a table, right? So start with this. X1 will be equal to what? The previous x0 minus the evaluation at x0 over the evaluation of the derivative at x0, okay? Now, what is x0? X0 is given, is here, right? X0 will be given, the starting point, right? The first value, x0. So you take it from there, your x0, right? It's here, here, here. That's x0. So the first calculation will be this. This guy, x1, will be equal to x0, which is -3, minus the function evaluated at -3 over the derivative evaluated at -3, right? This is the first value, x1. So, but for that, I need the function. My function is given here as x squared minus 4 cosine of x, right? This is the function. And I need its derivative. The derivative of this function is derivative of x squared twice x minus 4. Derivative of cosine is minus sine of x, right? Simplifying this derivative, I get this, twice x plus 4 sine of x, right? We're going to use this f of x and this f prime of x, right here and here. So how you use that? Well, if you go to your calculator, right? Your scientific calculator, then what you're going to get is this in your scientific calculator, right? -3 minus the function evaluated at -3. So I'm going to use a fraction here. The function evaluated at -3 will be -3 squared, -3 squared minus 4 times cosine of what? Of x, but x is -3, right? -3 radians, right? Don't forget, you have to work in radians. So click here, radians. Now, divided by what? Divided by the derivative, which is this guy, twice x. What's x? X is -3, right? -3 plus 4 4 times sine of -3, right? -3. Very good. So don't forget radians, right? Radians. Now what I get is negative 1.02574, right? This, you have to write it down somewhere, or you have to look for the one which gives you this, right? Which of these tables is giving you for x1 that value? Anyone could tell me? A, B, C, or D? Looking at this, look. X0 for all the tables is -3 because the initial point. But what is the next point, the x1? Look, it's not this, right? Here, you look at it, not this, not this. Look at this. It's this guy, right? You follow? So this means that the answer should be this. Now, of course, you can continue working, right, and get the other values, right? I can do one more for you to see, right? But we gotta do this if you want to continue with it. Notice that they are asking you here to round it to how many decimal places? 5 digits, right? 5 decimal places. So that's what we're gonna do. We're gonna take 5 decimal places and do the rounding. So 1, 2, 3, 4, 5. So up to 4, right? Yeah, great. So you should write this down. I'm gonna put this down and write down the result here, right? So this first point, this first result, we agree is negative 1.02574, right? This was our first computation, our first approximation to the root of this function, right? To the 0. Now, x2, let me show you in case you want to continue, right, with x2. x2 will be the previous x1 minus the function evaluated at x1 over the derivative evaluated at x1, right? But what will be that? Well, it will be this guy that we got rounding to 5 decimal places, right? 74 minus, remember, the function evaluated at this guy, right? It's an iterative method, right? Which means that the output becomes the input for the next computation, right? The derivative of this guy. But now, in class, remember when we cover this part, I show you a nice trick to work this out efficiently, right? It's a long number. So if you hold this right here, you're in your decimal calculator, right? I did this computation with -3, right? So what do I have to do here to get this done? Just wherever you see -3, instead write this new number, the negative 1.02574, right? 574, right? And to make it even easier, just copy and paste this, right? Capture this, paste it here, right? Wherever you see -3, now you replace it with the new value, right? With this guy. Again, -3 here. Again, this. -3 here, again, this, right? And you get now a new value, negative 1.21246, right? Follow? Rounded to 5 decimal places. Now that guy has to be here, right? The x2, right? The x2, look, notice is exactly that negative 1.21246, right? Is this guy. You see it? But it was enough, one computation to get it, right? You see it, guys? So you're not gonna have to go to the whole table of the exam, right? The exam, one question I think is gonna be based on the Newton's method, right? But what I'm trying to say is that you don't have to go through the whole 5 computation, right? 2 or 3 would be enough, or even 1, as you can see right here, only one table had the first computation. So this was the second x2, right? And similarly, you can get x3, x4, and so on, right? And then I will put dot, dot, dot. You continue, and then you can get the rest. But you can notice that with this one, to the first computation, with x1, you should be able to identify the table right there. Eventually, it gets stabilized. So at the step 3, you will get the same answer. So it doesn't make sense to continue. Yeah, go ahead. A question? Mm-hmm. Yeah, very good, with excellent. Yeah, let's do one more probably, right? For you to see that it's not difficult. For example, this I did it in class, I think. Let's look for a new form. Let's say this cubic polynomial. Like you see 10 computations, professor, 10 iterations. Don't freak out, guys, because it will take just 2 or 3 iterations to get it. You will see. Look, this one, again, right? Newton's method says xn plus 1 is equal to xn, the previous, minus f evaluated at xn over the derivative evaluated at xn. So, which means that x1 will be the previous x0 minus f evaluated at x0 over f prime, the derivative evaluated at x0. But what is x0? X0, they will give it to you always. The initial value, the initial guess, 1, right, is 1. So we say, okay, this will be 1 minus the function evaluated at 1 divided by the derivative evaluated at 1, right? Let's see what is this. Now, the function here is clearly this cubic function, x cubed plus x minus 9. And the derivative of this guy is simply this, 3x squared plus 1, right? That's its derivative. Now, let's compute this in a calculator then, right? Let's bring our Desmos calculator and let's do net 1, right? 1 minus the fraction, this fraction, the evaluation of the function on the top, and allow me to use parentheses and do 1 cube. And you may say, right, Professor, but 1 cube is 1. Yeah, I'm just doing this because later, remember, we're going to just substitute wherever we see 1 within parentheses, the new value, right? So it's like an efficient way to get this done. And on the bottom, 3 parentheses, 1 square plus 1, right? There you see. The first value, 2.75, right? 2.75 is the first value. Now, don't close this, right? Just put it down for a moment, right? We're going to use it again. So put it down somewhere. And then you see that this was 2.75, right? 2.75. So let's write it out here. 2.75. The first value, the first approximation, 2.75. Okay. Then you look through here, right? The first one is 1, is known, right? 1. All the tables have 1. But then you look at the tables that have 2.71 for the second choice. So we're talking about this table or this table, right? Cannot be this, cannot be this. So we already narrow it down to 2 tables, these 2, right? So let's go one step ahead. So now x2 will be equal to what? x2 will be equal to x1 minus f of x1 over the derivative evaluated at x1, right? So meaning what? 2.75, which is the new value, right? The output becomes the input, right? F evaluated at 2.75, sorry, over the derivative of the function at 2.75. But what is that? Let's see. Well, if you go back to Desmos, right? For a reason we held it here this way, right? Just where you see 1, write instead the new input value 2.75, right? For the new iteration. So here 2.75, right? You can copy and paste, right? Or type it 275 right there. 275 cube, right? Within parentheses, right? So we can do the next if needed. All right, so then this was cube. Okay, cube, then 275 again here. 275 again here. And the new value is 2.13588. Let's see how many digits they want. They want, I think, in this particular problem, 6 decimal places, 6 decimal places. So make sure you write this up to 6 decimal places, right? So we're going to do that. So this will be 2.13588. And then you have a 3 and 9, right? 3 and 9. That's it. Yeah, 84 then. So 135,884. 2.135,884. So put this down here, and this guy should be 2.13, right? 2.1358884, right? So that's my x2, right? My x2. So look at the tables now. Which one is showing that? Anybody could tell me what is the table that you have to choose then? Anybody in the chat? Close this. Yeah, very good, very good. Excellent. So it took 2 trials, right? Two. Zoraida, very good. Zoraida, Illinois, Tiffany, right? Yeah, it's not hard to see that this is the one. We say, why, Professor, you are taking this table? Well, this is good, right? The first one is 1 for all the tables. This was good. This is this guy, right? And the third one has to be this, right? And the only table I show in that is this, right? And eventually gets stabilized, so don't get freaked out. So this is it. And then you choose this as your answer, right?